Okay, we're now going to solve an example problem involving a control volume moving at a constant velocity. So I'll begin by drawing out the problem itself. Okay, so what we have here is we have a water jet, and the jet of water is flowing from the left to the right in this direction here, and it is impinging upon a blade, and that blade is on rollers, and consequently it is free to move to the right due to the fact that this jet or water jet is impinging upon the blade. And so what we are told to solve for in this problem, we're told to find the force So we're told to find the force on the vane in order to keep U constant. So essentially what we're told is what is the force required on the vane. So this is our vane here. There will have to be some force, and we don't know exactly which direction it's going to be moving in. But a force something like that. Let me clean it up a little bit. That's not the nicest vector. But we have some force that we're looking for, and the purpose is to find for U to be constant, and consequently that would be a case of a control volume moving at constant velocity, because you can probably figure out we're going to put the control volume around the vane. Things that are given, we're told that the velocity of the cart to begin with is 10 meters per second, and that's the velocity that we want to maintain. And the jet is coming in at a higher velocity. It's coming in at 30 meters per second. So this is a case where we will be doing analysis using a control volume moving at constant velocity. So let's take a look at the solution. Okay, so what we have here, this is what our problem looks like. We have the cart is moving at velocity u, and I'll draw that as a vector going in that direction. The jet is coming in from the left. Now what we're going to do, we need to specify the control volume. And for this problem, what we're going to want to do is have the fluid crossing the control volume perpendicular to the control volume itself. So we will draw the control volume like that so that it is perpendicular to the fluid streams. And then I'll come over here. The control volume, I'll bring it right down to the ground, but it's not going to go to the ground exactly. And then I will bring it up. So this is our control volume that we will define. And what I'm going to do, given that we have fluid crossing this boundary and this boundary, I'm going to call this control surface 1, and this will be control surface 2. And then the last thing, well, another thing that we'll do, remember, this is a control volume that is moving. And so it's moving. We have a moving reference frame. We'll give that a little x and a little y. And what we're going to do, just that you can picture what's going on, we're going to draw a little person on here, because that person is moving with the control volume. And then finally, we're going to look for a force in order to maintain the velocity u at a constant value. And we will have a reaction force in the y direction and a reaction force in the x. And I've just drawn them in that way, positive x, positive y. We'll have to see by the sign that we get when we're done which direction they actually go in, which is kind of a typical thing that you always do in statics. So we have the fluid coming in. The basic equations that we have, the basic equations that we'll be using will be a conservation of mass or continuity and the momentum equation. And so those will be the two basic equations. A few assumptions. Let me write out the assumptions before we jump into the equations. Okay, so a few assumptions that we have steady flow. So even though the control volume is moving, it's not accelerating because the force is holding it so that it only moves at a constant velocity. And the conditions coming out of the jet itself from here, we're not told anything is changing there. So as far as we're concerned, we can assume that to be steady flow coming in. Uniform flow. So what does that mean? What that means is that we're going to assume that this is kind of a fixed velocity profile. If you're to look at the velocity profile coming in, it is uniform. It's not a velocity profile that would have some sort of parabolic or different type of shape like that. We're going to assume it to be a uniform velocity profile. Sometimes we call that the top hat profile. Because it would be flat. Neglect body forces. Next thing, density is constant, so incompressible flow is what we're dealing with. And the final assumption is that V1 is equal to V2. And so what that is implying, the magnitude of V1 is equal to V2. So that would be the velocity of the fluid coming in at control surface 1 and the velocity or the magnitude of the velocity of fluid leaving control surface 2. Okay, so those are the assumptions. What we're now going to do, let's move ahead and start working with our basic equations. Okay, so we have linear momentum and we have continuity. So those are the basic equations, continuity. Basic equations we have, let's start with continuity and applying the assumptions that we wrote out. We can eliminate some of the terms. So okay, so to begin with, we have steady flow. So this guy is gone. And what we're left with is an integral across the two control surfaces. If we look back here, we have control surface 1 and control surface 2. So we apply the continuity equation across those two control surfaces, and let's expand that out. And I'm going to write the velocity vector with xyz, so that's in our, with respect to the control volume reference frame. I'm going to put it with a little subscript 1. And then for control surface 2, we have that. Now, writing out the velocity vector, or the, that'll be the velocity vector at control surface 1. What we have, looking back, and remember we have to deal with velocity with respect to the control volume. So we have a situation where we have V coming in, and the control volume itself is moving at U. So the velocity coming across here with respect to the control volume is going to be the difference between those two. So we will have V minus U, and then we can express that on inlet. Both components are moving in the x direction, and so we get this. I can write it out in the I component. Then for the velocity leaving, this is for one of the assumptions we had. We said that the magnitude of the velocities were the same. So looking back at our drawing, we know the angle here is 60 degrees. So we can use trigonometry to figure out what the velocity component would be leaving. So that would be the x component. And the y component. And there we've made use of the fact that the magnitude of V1 is equal to magnitude of V2, one of our assumptions. So what we can do is we can put this together, and what we get for continuity, And remember, we need to be careful with the sign here. So for control surface 1, let me just sketch this out because this is sometimes an area where students have difficulty. So for control surface 1, let me draw the area. Remember, the area vector is always going to be going outward from your control surface, so that's the control surface. But we have a velocity that is moving in this direction. Actually, it's the v minus u. And so with that, this is going to be a negative. And then for control surface 2, what we had a control surface that was angled. Again, the area vector is moving in that direction. And then we have the, well, I'll just draw it as a vector, but our velocity vector is going to be going in the same direction, and so that will be a positive. So consequently, what we get from the continuity equation is the following. And from this, density cancels out because we're dealing with incompressible flow. And we don't know anything about area 2, so I'll just leave that as area 2. But we get the magnitude of xyz at interface 1, control surface 1 times area 1 is equal to the magnitude of velocity at control surface 2 times area 2. So that's what continuity gives us. We're going to park that and then move on to take a look at the linear momentum equation in the next segment.